Good afternoon, everyone. Hope that you guys enjoyed your extended weekend, and I hope that you are so far getting ready for your second week of classes and feeling good about that. Um, I've got us recording now, so I'm going to go ahead and get moving on this. So, if you remember last week, one of the things that we talked about was we talked about kind of a foundation, a little bit of a crash course in general chemistry. And this week, what we're going to do is we're going to kind of take that next step. I've got all of the PowerPoints that we're going to be using posted up for the first exam, which I think our first exam is a Monday, the 17th. Does that sound right? No, that would be a Tuesday. Yeah, Tuesday the 17th, sorry. Um, so we're going to work through all these and just kind of, yeah, get ready for that exam. And I'm gonna have a review sheet and a review guide for y'all. Um, so those are big items. Um, so I just wanted to kind of get you up to date on that. Now, with that in mind, um, the first thing that we're going to talk about is bonding. If you remember last week, we talked about two different types of bonding, ionic and covalent slash molecular bonding. And we talked about basically um, sharing of electrons. And I'm just going to label electrons as E minus, or I'm going to switch it to donating electrons. Okay, so those are two different types of bonding. Now, there's another type of interactions that we'll refer to as intermolecular. Now, the big difference or the big thing here is inter versus intramolecular. So, ionic and covalent, these are both examples of, it's weird. These are both examples of intramolecular. Um, whereas intermolecular is basically the types of interactions that take place between different molecules. So, one example, and the one that we're going to focus on as our kind of highest priority. Can everyone hear me all right? I just want to make sure I'm using a different microphone this week. Can I get a thumbs up in the chat or something in the chat to say you can hear me? Okay, thank you. Yeah. So this type of bonding is known as hydrogen bonding. Now, hydrogen bonding is going to require two things, a hydrogen bond acceptor and a hydrogen bond donor. So, what a hydrogen bond looks like is I'll go ahead and draw this molecule right here. So, this is one molecule, and here is another molecule, another identical molecule. It's going to look a little bit different, and that's essential for kind of the demonstration of what we're talking about here. Um, but both of these are C3 or CH3OH. CH3OH. Now, each of these oxygens has what is known as a lone pair or two lone pairs of electrons. So these lone pairs of electrons are pretty critical for understanding hydrogen bonding. And adding to that, these groups, this right here and this right here, are essential for hydrogen bonding and understanding hydrogen bonding. Now, for hydrogen bonding to occur, what we have to have is we have to have two groups with a hydrogen, a nitrogen, an oxygen, or a fluorine. So, in order for hydrogen bonding to take place, these atoms right here are essential for H bonding or hydrogen bonding to occur. Now, one is pretty obvious hydrogen has to be present, but nitrogen, oxygen, and fluorine, all of these atoms are going to have lone pairs of electrons. Now, what I'm about to draw is an example of a hydrogen bond. A dashed line typically denotes a hydrogen bond. Now, when it comes to this terminology, hydrogen bond acceptor and a hydrogen bond donor, well, one of these things is going to be donating a hydrogen bond, and that is the substance with the hydrogen. The other group is going to be a hydrogen bond acceptor. So in this case, both OHs are hydrogen bond donors and hydrogen bond acceptors. The question is, well, which group is which? And you really figuring this out from the perspective. So molecule A and molecule B. Molecule A is our hydrogen bond donor, and molecule B is our hydrogen bond acceptor. That's all there is to hydrogen bonding. Now, things that you need to know for this and essential things for this particular slide. One, know which atoms are essential for hydrogen bonding. So if I showed you something like this, no worries. I just got that message about Wi-Fi troubles. Don't worry about it. I've recorded, or I'm recording, so I'm going to make sure that I'm recording. Yep. So you'll be able to review the first little bit of the class. Okay. So we've got these two molecules right here, CH4 and CH4. My question is, can hydrogen bonding exist between these two molecules? Let's go ahead and let's think about this. In order for hydrogen bonding to occur, we have to have a hydrogen. Do each of these molecules have a hydrogen? Yes. So that's part one. The next part is we have to have a nitrogen, oxygen, and I'm going to label this or a fluorine. Do we have a nitrogen in either one of these molecules? Nope. Do we have an oxygen in either one of these molecules? Nope. Do we have a fluorine in either one of them? No. So now add to the chat, can hydrogen bonding exist between these two molecules? No, you're absolutely right. It cannot be, these two molecules are not going to have hydrogen bonding going on between them. You're absolutely right. That's great. Okay, so what you really need to think about is those four atoms. Hydrogen, essential for hydrogen bonding. Nitrogen, oxygen, or fluorine must also be present for hydrogen bonding to take place. So if you keep that straight, you're going to be in great shape. Then the next thing is when we look at a hydrogen bonding pair like what is shown here, then I could ask which one's the donor, which one's the acceptor. Well, which one basically has the hydrogen that is being shared? This hydrogen is the one that's being shared. Therefore, this is the hydrogen bond right here. So this molecule, molecule A, is the hydrogen bond donor. Now, molecule B could also be a hydrogen bond donor, but that's not how we have it drawn. How we have it depicted is an important part of this. Okay. Does anyone have any questions about hydrogen bonding and hydrogen bond donors or acceptors. The last thing that I want you to know about this slide is also what's the difference between inter and intramolecular? Expect questions, or you can expect a question like this is an example of intramolecular bonding. This is an example of intermolecular. So hydrogen bonding is your example of an intermolecular force. Okay, so that's going to be super important because what we're trying to do is we're trying to figure out how to design a drug and we're trying to basically make a drug out of something. So the question is, what makes a molecule drug-like? And in order for something to be considered drug-like, the molecule must satisfy Lipinski's rule of five. Now, one thing that's a little bit tricky is rule of five. I think that it's pretty common to hear that and think, oh, five rules. No, it's the rule of five. Okay. So this is called the rule of five because the criteria are in multiples of five. So in Lipinski's rule of five, there are no more than five hydrogen bond donors. And that's no more than five hydrogen bond donors. There are no more than 10 bond acceptors. The molecular mass of less than 500 Daltons. Yes, I'm sorry, I got a side chat. Intermolecular is the force acting between molecules. Absolutely. Whenever I always think of inter and intra, which one is which. I always think about the interstate. Interstate 35 goes between states. That's the intent to take you from Texas to Oklahoma if you have to go to Oklahoma. I guess what would be a better example? I don't know. Texas to Northwest Arkansas. That's beautiful up there. Anyway, but that's not Interstate 35. So intermolecular between two molecules. Okay, so then number three here. So Lipinski's rule of five, our rule of five hydrogen bond donors, no more than 10 hydrogen bond acceptors, and a molecular mass of less than 500 Daltons. Okay. Now, a molecular mass. In your 1310 class, you talk about calculating molecular mass and you use terms like 1 or 12 grams per mole. Okay. Well, 1 Dalton is 1 gram per mole. Okay. Then number four, the octanol water partition coefficient, also known as the log five or log P, is less than five. Okay, so there's our last five. So oh man, we've got four rules, all kind of related to five. We're going to look at each one of these in just a second. But by the time we finish this or by the time we finish today's section, you should be able to tell why Tylenol satisfies Lipinski's rule of five. Okay, so we're going to dissect each one of these. First one, no more than five hydrogen bond donors. Now, if we jog back for a second, that means we can't have no more than five of these. Okay. Now, what that means is be on the lookout for nitrogen hydrogen and oxygen hydrogen bonds. Because when you think about a hydrogen bond, you should see, well, there's got to be a hydrogen, but then there's also got to be a nitrogen, oxygen, and fluorine. Could there be a fluorine hydrogen? Yeah, but it's much less likely. So this takes, our criteria for hydrogen bonding and really kind of makes it a little bit more narrow. We're looking for nitrogen hydrogen or oxygen hydrogen. Now, a key detail is that this does not mean no more than five hydrogens because there's going to be, tons of hydrogens on a molecule. Specifically, what you need to look for is nitrogen hydrogen and oxygen hydrogen. When you see those, you'll be able to see, well, is there a hydrogen bond here? Now, this is the first five. So, of our rule of five, we've got no more than five hydrogen bonds. So, this is our first one. Next one, no more than 10 hydrogen bond acceptors. So if we jog back, no more than fewer than 10 of these. So now I can go back. So again, be on the lookout for nitrogen and oxygen atoms because those two players are the most likely to be involved in hydrogen bonding. Now, this is our second five. Well, it's not really a five, but it's divisible by five. So 5 times 2 is 10. So that's where 10 hydrogen bond acceptors. So no more than 5 donors, no more than 10 acceptors. Now, with that in mind, these first two rules of five, if you look at a molecule, you can identify an acceptor and a donor. Now, this is going to take practice, but that's what's going to be on your quizzes that are up on your Canvas page. Now, our third one is a molecular mass less than 500 Daltons. First of all, 500 Daltons is the same as 500 grams per mole because 1 Dalton is 1 gram per mole. This is our third five. Of our rule of five, this is our third one. Okay, so again, if we look at a molecule, we can calculate what the molecular mass is and determine is it more or less than 500. So these first three things, hydrogen bond donors, hydrogen bond acceptors, and molecular mass of less than 500 Daltons. These can all be determined by looking at and investigating a molecule. Now, our third one, or our fourth one, I'm sorry, an octanol water partition coefficient. I tried to make that one word. An octanol water partition coefficient, or a log P, less than 5. Log P. Well, first of all, let's go ahead and roll back a second. Octanol and water. These are two substances that they don't mix with one another because they're different from one another. These are kind of like oil and water. They're not going to mix well. Now, what that means is when you add a compound to octanol and water, that compound is either going to go into the water or it's going to go into the octanol. Now, log P indicates how soluble a molecule is in water compared to the solubility of a molecule in fats or lipids. Now, this is determined experimentally. Does the drug go into the water or into the octanol? This is quantitated and ideally has a range between -1 and 5. So think about this as being this log P has a value from, let's say, -10 all the way up to +10. Again, this right here, it is determined experimentally. That's a key part of this. So when you look at a molecule, you can't look at it and say, aha, it has an octanol water partition coefficient of 6.4. You can't look at a molecule and deduce that. This is an answer. This is a value that I will always give to you. Now, what I want you to know is I want you to know, yeah, it should be less than 5, but its ideal range is going to be between -1 and 5. Now, when a drug is administered orally, it's going to have an octanol water partition coefficient of between 0 and 3. Drugs that are administered through an IV or intravenously can have a wider range. So they can be greater than 5. Drugs for the central nervous system capable of crossing the blood-brain barrier need a higher log P. Okay, so this is all about, well, something dissolves in water. That doesn't mean that it's necessarily going to get to a cell. And so, or it's going to get to the right cell because every cell is going to have like a membrane surrounding it. And so something might go into the cells of the or the intestine, but not necessarily of another organ system. So, what I want you to know about this is first of all, it should be lower than 5. The ideal range is -1, +5. Orally administered drugs typically are 0 to 3. If something's delivered by an IV, it can have a higher log P. And drugs that a higher log P is a hallmark of a drug for the central nervous system. Those are the details that I want you to know about this particular value. In addition to that, I will always give you this value whenever you're evaluating a molecule for its ability to, or for whether or not it satisfies the rule of 5. Okay. Now, does anyone have any questions about this right here? If you have a question, feel free to add it to the chat. You can either send me a direct message or send it to the entire group, and I will do my best to answer it as soon as possible. Now, with that in mind, I'm sorry, just one moment. Okay, so with these, yeah, and we're going to look at a couple of molecules and see if they satisfy the rule of 5. All right. Now, here we go. Organic chemistry. Now, we need to understand organic molecules before we can actually design any sort of drug. So we're going to get into organic chemistry and how relevant it is to drug discovery. So, where did those disappear to? Oh no. Boy, that makes it really difficult. Just a second, everyone. Now, okay, this is okay. I gotta pause for a second. This is my I came back to this picture just because I wanted you to see this figure. And this is what I'm meaning about. You put your potential drug and you see, does it go down here with your octanol or does it stay up here with your water? Actually, this would be octanol, and this would be just an example of what this process looks like. Does it go with the octanol? Does it go with the water? And that's and based on how much ends up in each place, that's how you would evaluate your octanol water partitioning and give it that log P value of less than 5. Okay, so organic chemistry. Now, this is defined as chemistry of hydrocarbons and their derivatives. Of tens of millions of known compounds, over 95% are compounds of carbon. Organic chemistry is a uh, field that is a very important field for the oil and gas industry. Um, in addition to oil and gas, it's also important for drug discovery and drug development. Um, these are super important for, and understanding organic chemistry is super important for understanding how people live and how they don't live. But it's also a big field for the oil and gas industry because gasoline and all their other similar products end up, well, they are made up of carbon. Carbon is unique in that carbon atoms can bond to each other and form long chains and rings, and a carbon atom will always bond 4 times. Now, a carbon atom, basically, it looks like this. Here's where it bonds 4 times. That's where it bonds 4 times. And that's where it bonds 4 times. Carbons always do this. They can have 4 single bonds, 1 double bond, and 2 single bonds, or 2 double bonds. Now, commonly found atoms associated with carbon are oxygen, oh, hydrogen, nitrogen, sulfur, and a class of compounds known as halogens. Now, if you remember our first meeting, we talked about, well, here's the periodic table, but what are the atoms that we care about? Well, we cared primarily about carbon, nitrogen, oxygen, hydrogen, and your halogens. Now, some good examples of organic compounds are ATP. Now, if anyone's taken a biology class or anything like that, or a science class in high school or anything like that, um, does anyone know where ATP is produced in a cell? I'll give you a hint. It's in the powerhouse of the cell. What is the powerhouse of the cell? The mitochondria. Perfect. ATP is generated in the mitochondria. This is what ATP looks like. It's got this molecule right here, known as adenine. It's got this part right here, which is a sugar. And then it's got this right here, which is known as triphosphate or three phosphates. Now, when you look at this molecule, I want you to kind of be thinking, okay, well, is hydrogen, does this have the ability to hydrogen bond? It does. There's lots of hydrogens, lots of oxygens, and when we're looking for a compound that hydrogen bonds, we're looking for oxygens and hydrogens. Next up, we've got caffeine. Now, what's not shown here is this right here. I'm going to go ahead and write CH3 because that's the convention whenever you're drawing a CH3. You don't have to draw the CH3, but instead you just draw a single line pointing outward. Then last but not least, glucose. Glucose is a 6-carbon molecule. There's lots of hydrogens, lots of oxygens, and it's a good candidate for hydrogen bonding. Now, when it comes to carbon properties, how many bonds can carbon form? Up to 4, or as few as 2 double bonds. Um, so it could form 2 double bonds, 1 double and 2 singles, or 4 singles. Now, what is the electron configuration of carbon? Well, when it comes to electron configuration, what we want to know about and what we're focused on is carbon and its hybridization and its bonding, that not intramolecular. Carbon can experience the following hybridizations. If you remember, we had sp, sp2, and sp3. Now I want to draw sp2 hybridized carbon. Looks like that. Carbon is bound to 2 different things. I'm going to label these X and Y. Next, so this would be sp because here's one thing, here's a second thing. sp2 would look something like this. X, Y, Y. So how many things is this bound to? 1, 2, and 3. So that is 3 things. So S, P, P. So it's sp3. This is sp. Last but not least is C, X, 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 X. So this is bound to 1, 2, 3, 4. So it's S plus P plus P plus P equals, oh, sorry about that. This is sp2. This is sp3. So this is the sort of question that you should be able to answer. How many things is that carbon bound to? Therefore, what is its hybridization? Oh. Now, does anyone have any questions about carbon and its properties? Okay, great. Now, there's a number of different categories of organic compounds. There's hydrocarbons. Within the group of hydrocarbons, there's aliphatic compounds. Aliphatic compounds are primarily carbons and hydrogens. Their examples of these are alkanes, alkenes, alkynes. We're going to get into those next week. Aromatic compounds. These guys are cyclic. And last but not least are your halogenated hydrocarbons, which these are, well, a hydrocarbon plus chlorine, or Cl. Chlorine or bromine is another halogen. Other categories include alcohols, phenols, ethers, esters, aldehydes, ketones, carboxylic acids, amines, amides, alkaloids, and more. Which are we going to focus on? These right here. Will we talk about others periodically? Do you need to be able to reproduce this list of organic compounds? You don't. I'm not expecting that. What I want you to know about is I want you to know about these listed here. Or sorry, what I want you to know about are the ones that we go into with a deeper appreciation, higher priority. That's what I want you to be familiar with. But like I said, we're going to visit them individually as we encounter them. Now, when it comes to organic molecule names, there's a convention and there's a strategy that's employed for naming them. And it's all based on the number of the number of carbon atoms that are in that molecule. So what we do is we count up the number of carbons in the longest chain. We say, okay, well, that is a chain of 3 carbons. That is prop. We're going to use the prefix or the stem of prop. If it has 5 carbons, it's going to be pent, 6, hex, 7, hept, 8, oct, 9, non, 10, dec. So if you were to see something like nonamide, well, then you'd say, okay, well, based on the prefix of non, it has 9 carbons. Pentanoic acid has 5 carbons. Now, I think that some of these things you've probably heard or observed in outside life or outside of the classroom. For instance, if you're going to go over to your friend's house and grill burgers or something like that, they either have a wood um, grill, or if they're fans of the TV show King of the Hill, they've got a propane, or they use propane and propane accessories. So they got a propane tank to, well, basically cook up their burgers. Now, there are a couple of different ways that you can denote an organic compound. One is with the what is known as the molecular formula. The molecular formula tells you the identity of the atoms and how many of each atom are in that compound. So these 3 different identifiers tell you or are describing the exact same compound. So C2H6 is the same as CH3CH2OH, which is the same as this structure right here. The difference is basically just the simplistic organization of them. These have different terms associated with them. You have the molecular formula, you have the condensed form, and you have the complete structural formula. There's also the last one is known as skeletal structure. Now, the skeletal structure gives a little bit of an idea of where atoms are spatially. I like using that word. I'm going to put in parentheses in space. So this depiction right here is saying that this end to that line and that point right there are both carbons. And those carbons are away from one another. So another way to draw this molecule would be like this. This carbon right here is above, in some respects, above this carbon right there. They are in different spaces. Okay. Does anyone have any questions about that? Well, if there are no questions, what I'd like to do, oh, chat. Okay. What I'd like to do is take a minute and, look at some of these different compounds. So we're going to apply Lipinski's rule of five to each one of these compounds and see, does this meet the criteria? So first, let's look at ATP. And let's go ahead and recount our rule of five. Number one, oh, darn it. One, fewer than five. What was it? Donors or acceptors? I think it was acceptors. Yeah, donors. Then two is fewer than 10 acceptors. And then third is, I'm going to say a molecular weight or an MW of less than 500 Daltons. Okay, so let's go ahead and do one, fewer than 5 hydrogen bond donors. So essentially what we're looking for there, oh, Chad, you're absolutely right. It does not meet the criteria. What was somebody sent a direct message that it does not meet the criteria. What was the first clue that you got?
Oh, hello.
Yes,
Well, it didn't have no more than five hydrogen bond donors.
perfect. So what did you look at to kind of get that clue about what did you count, I guess? Was there a particular group that you're like, aha, I'm going to count those up and I'll be able to answer it?
Um, I, I kind of I think I've worked with this before, so I kind of just I didn't actually I've worked with ATP, so I knew that it didn't have to meet the
Okay.
criteria.
Okay. Well, I'm going to go ahead. That's awesome. Great job. So we've got, if you're looking for these donors, what you could do is one thing that you can look for is OH. One, two, three, four, five, six. And then the other donor that we could look for is an NH. There we go. So we've got a total of seven donors. So we don't have, it doesn't meet from that standpoint. So I'm going to write seven H donors. Okay. Then next is, all right, well, the next thing that we're looking for is 10 acceptors. Okay. So when it comes to something that accepts electrons, I mean, heck, what we're looking for is a nitrogen and an oxygen. Well, each one of these that I've already circled could act as an acceptor. It depends on the other species that's in that same solution. In addition to that, this nitrogen I'm going to circle, it looks like this: two bonds, single bond, and then a lone pair of electrons. That lone pair of electrons means that if something else floats around, let's say water. Oh wait, I got to do some erasing real quick. We could have a hydrogen bond between that hydrogen and that lone pair of electrons. So this could also be an acceptor because that nitrogen with that lone pair of electrons is going to be an acceptor. So that would mean that's an acceptor, that's an acceptor, that's an acceptor. That could potentially be an acceptor, as could a double bonded oxygen. So this. So we're looking at, let's see, if we had seven donors, our eighth, 9, 10, 11, 12, 13, and then every single one of these oxygens, we're looking at like 13 acceptors. I'm going to say 13 plus acceptors. So, I mean, we're 0 for 2 right now. In terms of molecular weight, well, that would be going to the periodic table. Oh, that's a great question, Alondra. Are the oxygens that are double bonded also going to be eligible? These could also be eligible. So that would be 14, 15, 16. So if you see that double bond, so this right here, so these are our two kind of depictions, and both of those can act as hydrogen bond acceptors as well. So that's a great question. I'm happy that you asked that because I didn't identify those, but they are still potentially acceptors. Now, number three, okay, let's go ahead and say we can calculate our molar mass or our molecular weight. I'm going to erase this. And what I'm going to do is I'm going to say hydrogen, phosphorus, oxygen, carbon, and nitrogen. Okay, hydrogen has a mass of 1. Phosphorus has a mass of 31. Oxygen has a mass of 16. Carbon has a mass of 12. And nitrogen has a mass of 14. Okay, so what I'm going to do first is I'm going to see I got 3 phosphorus. So I'm going to multiply this by 3. Hydrogens, I've got 1, 2, 3, 4, 5, 6, 7, 8. And then what's not shown here is at each one of these points, I'm going to do some more erasing. At each one of these points, that's a carbon, and that has additional hydrogens. So let's see, where are we at? Okay, so I had, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So I got times 17. Oxygen, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 oxygens. Okay, so I'm going to do the math real quick on these. I'm going to pull this up on my calculator. I've got 17, then 31 times 3 be 93. Then 16 times be 208 carbons. I gotta add all these up. Okay, so carbons, I gotta do some more erasing. And when we're looking at this, I just want you to know that if you see a question like this on an exam, I will more explicitly include every single atom. So you're not going to have to look at it and be like, oh, there's a hydrogen there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10. So that's 120. Nitrogen, I've got 1, 2, 3, 4, 5. So 5. Okay, so 14 times 5 is going to be 70. So 70 plus 17 plus 93 plus 208 plus 120 plus 70. So our total molar mass or our molecular weight is 578 daltons. So ATP, for example, doesn't qualify or doesn't satisfy any of our rules of 5. In fact, it's a violation of those first 4 or first 3. So do we even have to look at the log P? Not really. Um, and but if I were to ask this sort of question, I would give you a structure and I'd say, does this satisfy the law of 5? Well, this one, first, no. Second, no. Third, no. I didn't provide you with the log P value, but spoiler alert, it also does not satisfy it because it's way too low. Okay. Caffeine is the same sort of process where you look at it and you just kind of do this calculation. Now, my question for you is lower molecular weight. Do you think that this molecule has a lower molecular weight than ATP? If we look at it, we say there's one, two, three, four nitrogens, one, two, three, four, five, six, seven, eight carbons, then oxygens. Who thinks that this has a molar or molecular weight greater than 500? And add to the chat if you think that it has a molecular weight less than 500. So we can look at nitrogen and just say, well, nitrogen has a mass of 14. So 4 times 4 is 56. Carbon is 12. So I'm going to go ahead and say 8 times 12 is 96. And then oxygen is 16. So 2 times 16 is 32. So we don't even have to account for the hydrogens. If we did, that's like 12 or something like that. 56 plus 96. Well, that would be 156 plus 32 is 188. So that's right, Bella. So by comparison to, so if we look at the molecular weight, well, caffeine does count as a drug based on that criteria. Our other criteria, maybe a little bit less dicey, or maybe a little bit more dicey, a little bit less uncertain, less sure. Then you can do the same thing with glucose. Glucose, looking at that, we've got one, two, three, four, five, six. Well, five of those are going to be hydrogen bond donors. So, rule number one, five donors. Less than that, that's pretty close. You got exactly five. Number two, 10 acceptors. Then you've got, well, six acceptors. You don't have 10, so it checks out there. Carbons, one, two, three, four, five, six. 6 times 12 is our mass for carbon. That's where that 12 came from. That's the periodic table. Hydrogens, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1 times 12 equals 12, because 1 is the mass of each of our hydrogens. Then oxygen, we've got 1, 2, 3, 4, 5, 6. 6 times 16, 96. So our molecular weight of glucose is going to be 72 plus 12 is 84, plus 96. 84 plus 96 equals 180. So that's less. So number three, less than 500. That checks out. So two of our criteria fit. Now you can do the same thing with Tylenol. Now, this is all that I wanted to talk about today. Introduce these five rules and work through a couple of examples. What I want you to be thoughtful of and aware of is these are kind of the guiding principles. If something doesn't pass or if something doesn't check all of those boxes, does that mean that it's completely useless as a drug? No, it doesn't. It just means that it might be a drug for certain applications, but not for others. So something that might attain two of the four criteria might be good for the central nervous system, but not for IV administration. Um, so that's really what I kind of wanted to get after today. Um, I wanted to also mention that right now on your Canvas, you have two quizzes. One of them, and they're not quizzes, they're kind of quiz homework things. Um, they One of them has content, and the other one is just really to make sure that you are ready to use Proctorio. So one of them is not administered by Proctorio, but the other one is. The one that's administered by Proctorio, you've got like 5 attempts on it. I want you to think about this as, okay, this is this is the setting I'm going to be in when I take a test. Um, don't do that one when you're like walking through campus and you've got your phone on you. Don't do that because that's not really going to give the best representation, and you're probably going to not be able to actually enter the quiz. If the quiz asks you for a um, login code or something like that, that means you should try again and use a different browser because I'm not going to provide you with one, no, with a login code, but instead Proctorio is going to provide you with a login code. Um, and Proctorio is going to randomly generate that. So if you are asked for a code, that means Proctorio didn't start, which means you probably have a browser issue. So I would try a different browser. Okay. Well, if anyone has any questions, you're free to ask them. I'm going to go ahead and stop my recording.